609?
Yeah, no, not right now. Yeah.
Yes.
So the pseudo transpose, it's the whole equation of x transpose x inverse times x transpose, right? It's not just like when we switch in the assignment from normal inverse to pseudo inverse, we don't just replace the inverse sign with pseudo inverse, right? We replace the whole term before the y by pseudo inverse of x.
Yeah, the whole term in front of it is called the pseudo inverse.
X, okay.
Yeah.
Hey guys, so I'm going to be building a lecture today. No, so my name is Atom. You guys will see me sit on the second or third row a few times. And you might know that the valedictorian elections are sort of about to happen. I'm one of the people running for valedictorian. There's 5 of
All right, so with that, let's go back to.
Professor will actually be
Yeah, yeah, we go back to learning about machine learning. So far, we have seen linear classification, and over there we use this concept of a perceptron, right? But it turns out that if you put multiple perceptrons together and these perceptrons becomes what we call neurons in some sense, and then we have a neural network. Okay, so starting from today, we're going to spend 2 weeks talking about neural networks. Okay, you probably have seen neural networks from other courses, or if not, then in the news, it's everywhere. Yeah, you already seen figures, drawings of neural network with different nodes connected together, right? But here we're going to start from the very foundation. Okay, to talk about what motivates neural network, and then we talk about how it works and how to optimize neural networks, and eventually how does it learn. Yeah? So we have seen this perceptron before, just a single line like that. Yeah, I want everyone to be at this stage should be very comfortable with your perceptrons. Okay, and especially which side is the plus, which side is minus. Does it make a difference or not? It does. Yeah. So we happen to have this in this line this way, and that the right-hand side is the plus, and the left-hand side is minus. So okay, it could have been the other way around, depending on your perceptron. Okay. Now we know there's a problem with perceptron that we discussed already, which is that it has to be a linear boundary, right? And but what if we have data points that are not linearly separable? For example, x1, x2, like that. Let's say we have a bunch of minuses here, maybe a plus, and a bunch of pluses there. Let's say pluses here, and then corners like that. Yeah. Okay. You might see, well, maybe the true boundary may look something like this. Okay. Right. This could be the true boundary. Yeah. And what do we do with this? We have discussed what to do with this. Yeah. At least there are 2 different methods. Yeah. Someone can tell me what are the 2 methods? At least one of them. Yes? Yeah, sure. Yeah, one of them is the pocket algorithm. Okay. What's wrong with what's bad about it? Exactly, yeah. You can draw a line eventually, but then you will still misclassify many points. Yeah? Okay. You use pocket algorithm, you can get a decent solution, as decent as it can be, given that you use a linear separator, yeah, either a line or a hyperplane. But in general, you get a suboptimal solution. Yeah, that could be highly suboptimal if you have a lot of points that are across the division line. Yeah. That are misclassified. The other method that we discuss is, yeah, that's right, a nonlinear transform, right? We transform this space into another new space and hope that these points, when it's mapped to the new space, they are linearly separable. Then we can run our linear classifier on the new space. Yeah, once you find that separator, you map it back to this space. Yeah, we have done that. So nonlinear transform. For sure, this will be prime topics for the midterm, right? Or plus neural network as well, since we're going to finish covering neural network by the time. So example is, say you have a z vector that is maybe 1, x1, x2, x1 squared, x2 squared. Right? In that case, you're making a quadratic transformation, right? And initially you have a 2-dimensional space. Now you have a 4-dimensional space, right? This one is just a augmentation. So you transform the high-dimensional space, and hopefully in the high-dimensional space it is linear. Then you're all set. So, but what is the potential problem with this method of nonlinear transform? Someone else? That's right. You need to know ahead of time what should be the nonlinear transform. So that means you have to have some domain knowledge about your problem. Yeah, you know that, okay, most likely it's going to be a circle, or most likely it's going to be parabola, and so on. All right? But very often you don't know. Yeah? So this one you need to know. I guess what transform to use. Ahead of time, that's the important point, ahead of time, yeah? before you see the data. You already need to know how to transform. So then naturally the question is there a way to do this without knowing the nonlinearity ahead of time? Okay? Is there a way for us to observe the data and then detect the nonlinearity? Right? If we can do that, then that's great. You know, we can observe the nonlinearity, the structure of the nonlinearity from our data, and then use that transform, and then transform it at the end. Then we do linear classification. Right? Okay. So to some extent, that's what neural network does. Okay. You all know the neural network is multiple layers until you get to the end, right? And the last layer usually is some kind of a logistic regression or linear regression or whatnot, okay? Or linear classification sometimes, yeah? But then the earlier layers, yes, what is it doing? Okay, well, essentially, it is transforming space, detecting some kind of pattern, what we call representation of the data, until you get to the last layer where you can actually have a linear separation, okay? So eventually that's what we're going to get to, okay? But for now, our observation as we gradually progress into a neural network is that given this kind of data points, okay, we can maybe represent those data points, these regions. We have 4 different regions, right? Maybe in terms of logical functions, okay? We can say that, well, over there, this or that location, they are pluses. And this or that location, they are minuses, okay? So that's a kind of an important observation. Just the same pluses, right? You know, I try to replicate those pluses, but not important. Doesn't have to be exact, yeah? So, you know, I can maybe, you know, divide space like that and say these regions, this region and that region, yeah? Or we can say this can be this or can be that, yeah? So after all, you know, they are just logical statements. We can express regions of space in space using logical functions. Okay, you know, things that you have seen before, yeah, the elm function, the OR function, and so on, right? Yeah, those are the logical functions. In particular, let's consider the following common ones. Yeah, y1 is let's say OR of, let's say the input is h1, h2. What they are, we're going to worry about later, okay? For now, let's say they are just logical inputs, right? They're Boolean variables. But since we have followed the convention to use -1 and +1, right? So our Boolean variables will be -1 + 1 instead of 0 and 1, yeah? Or you can call them true and false, right? But doesn't matter what you use to label them, yeah? They're just 2 different things, okay? That's all that you need to know, right? Binary inputs. And then these functions, of course, these functions will output, you know, based on the input logic, values, yeah. And usually you can you can write down a truth table, right, to represent these functions, yeah. You map whatever. There are 4 possible combinations of inputs, right? So there are 4 possible outputs for every one of them. So you should be very familiar with these Boolean functions and also Boolean algebra in general, right? I hope, yeah. So let's study the first one, OR, with h1, h2 like this, okay? How does it look? Or what does it look like? So here is h1, h2 as input, right? Yeah? And the input can be 1 or -1, yeah? -1 like that, right? Yes?
Would it be, so if, I mean, because it's like
Yeah.
Would it be that any positive combination is just positive, anything, so basically only the left quadrant, the left bottom quadrant
Yeah.
is negatives, and everything else.
Well, this is all function or all gate. So your input, your only 4 possible combinations of inputs. So only these 4 corners matter, yeah. And then you just figure out the values at those 4 corners. So if both of them are 1, both inputs are 1, then the all function would give you a plus, right? Yeah. I use a plus like that just because I want to draw it as a data point for you. Okay. This is one of your training data points essentially. Okay. And then over here, it's the all function is still plus, obviously. Yeah. I hope this is obvious to you, by this stage, right? 4th year of at least 400 level course. Yeah. So this one is the only one that's minus. Yeah. Because both of them are -1. Yeah. So this is the function, right? This is how we draw this function d equals to 2. Yeah. 2-dimensional function. Okay. Now, if I have to use a perceptron to represent this, can I? What would a perceptron look like if I want to use it to represent this set of data points? You already know, right? There are 2 sides, this side is plus, this side is minus. Any line, separate thing we do, right? Any line we do, yeah? That would be a perceptron that can give you this function, okay? So therefore, in fact, we can use a perceptron to construct this all function, yeah? Just by drawing that line, right? Anything that side plus, anything on this side minus. So in fact, I will say, well, let's draw a line that is like this. We follow the textbook's example. It draws one that has an intercept of -1.5, okay? You don't have to use this particular line, right? As I said, any line will do, yeah, as you also seen before, okay? But if I draw a line like that, what does the perceptron look like? Well, it's a sine function, right, of a weighted sum of the inputs, yeah? The inputs are H1 and H2 now, right? These are our inputs. So what does this line represent? Sine of, this line would be, well, this is 45 degrees, right? So the slope would be 45 degrees, and it's a 1, 1 for the weight. That's good enough, right? So H1 plus H2. What is the intercept? The intercept is -15, or 1.5, so therefore it's plus 1.5, right? This is the line. H1 plus H2 plus 1.5 equal to 0. Yeah? When I take the sign, I know that this side will be plus, that side is minus. Yeah? Okay? So everyone by now should be able to do this in your sleep. Yeah? You have seen perceptrons so often already. Yeah? You have seen it in your homework, you have seen it in class, you have seen it in your programming assignments. Okay? So again, this one is essentially H1 plus H2 plus 1.5 equals 0, right? That's the line. Yeah? And also we know that this side is the plus side. Yeah, for this sine function. Yeah, because the sine function, when it's positive, yeah, it's actually this side is the positive side. Okay. Yeah, and we can draw this perceptron as well, right? This perceptron has a activation. Let me draw a bit of circle. That is a sine function. It outputs this y hat 1, yeah? And then we have 3 inputs. The usual H1, H2, which is our regular input, and then we have the augmentation part, yeah? Or sometimes also called the bias term, yeah? And when we send this bias term, well, augmentation 1 in, but then what is the W value? W is the weight, right? What are the weights of these inputs? Well, for H1, H2, they're all both 1, yeah? The weight for H0 is 1.5, right? So we write 1.5 as the weight, right? Yeah? We usually do not write the weight of 1, yeah? So just to save some messy numbers later, because when we put into a big neural network, too many numbers to write, right? So, and that's the reason why we choose to use the coefficient of 1, just make it easier to draw. Yeah, you can use any line, right, in between that does not, cross over to the other side. Yeah, so you could have any kind of W you want, but we choose the simple one. 1.5, 1, and 1. That's our W. Yeah. Can everyone understand what I'm saying? The W is the vector 1.5, 1, 1. Yeah, that's our W. Right? Our input is the H, right, for this function. Okay, yeah? So now we show that we can use a perceptron to build an OR function. How about the other logical functions? How about the M function? Well, as you can imagine, it would be very similar, right? You just do the same thing. You draw this picture of the function. You make it a bit longer. H1, H2, 1 minus 1, 1 minus 1. Yeah? If they are both 1, the M, of course, gives you plus. Anywhere else, they give you minus, right? This is the M function. Of course, it looks like this, clearly. Yeah? Nobody should have issues with this, I hope. Yeah? And then how do you separate them? Well, let's say, again, we use the intercept 1.5, yeah, to draw this line. 1.5, like that. Again, you don't have to use 1.5. In this particular, you can use 1 or whatever. But I just want to follow the textbook so we don't stay too far away from it. Y2, let's say it's the N function. So it's what is this line now? Still, it's a H1, H2, yeah, because it's still the anti-symmetry or anti-diagonal line. Now the intercept is 1.5, so this is 1 minus 1.5, yeah? Okay. So if you observe the difference between the M function and the OR function for the perceptron in terms of the algebra, you see that the only difference is the intercept, yeah? You change from plus 1.5 to minus 1.5, yeah? In order to draw this perceptron, I can just copy and paste now, right? I already have this guy. All that I change is the weight for the H0 term, yeah? So all that I need is to put a minus 1.5 here. And that's an M function, right? Oops, I'll have to change this Y2 as well, of course. Yeah? Everyone okay so far? No, we will have to go to more complicated stuff. We have something that's more interesting. Yeah, because this is simple, I hope, right? Yeah. So, what about the exclusive OR? Not really a trap, yeah. It's slightly more complicated. When you draw the function, let's see what happens. H1, H2, again, 1, 1, minus 1, minus 1. If they're both 1, now exclusive OR give you what? Minus now, right? Exclusive OR. So only exactly one of them is 1, then you get plus, yeah? So plus, plus here, and then with the both minuses, and then you get minus, okay? Now you see this, what happens? What's wrong with this? Yeah, it's not linearly separable. Clearly, you cannot use a single perceptron to build this function anymore. Okay, ideas? What do we do now? Two lines, yeah. Yeah, we have to use 2 lines. That means you have to use 2 perceptrons at least, okay? But more than that, actually turns out that we need 3 of them, okay? So we have 2 lines, yeah? Let's say we just use the lines from before, yeah? Maybe let me use the blue one, why not? Yeah? This line there that we have before, and then we also have this line, right? The top one is the one that gave us the M function. The bottom one is the one that gave us the OR function, right? If we use the same thing as before, then we know that this one for the OR one, right? We have this one in that direction. It is plus, right? Yeah. For our line before, same as just the OR function, right? Above turns out to be plus in this case, and then for the above line, the line above, if we use the same perceptron as before, then going downwards is actually minus 1, yeah? If if I go this direction, well, maybe it should be more clear. I go this direction, then this is y2 hat equal to +1, yeah? So the opposite direction will be -1, yeah? Okay. So how do I represent this using perceptrons when I need two lines? Yeah? How do I combine, say, multiple of them? Yeah? That's right. So you have to say a negative of that. Yeah. Yeah, kind of, but not minus. But we have to use a Boolean algebra, right? So we only have and or and not, that kind of thing, right? So let's say this is or, but not and, right? That's the definition of exclusive or, right? Yeah, it is or but not and. Yeah, there's one way to define it anyways. Okay? If we have to write it in Boolean algebra, what is this equal to? How do we express no but not and? How do we express the English but? In minus? Not quite. Not is minus, yeah? Not is the complement, yeah? Conditional? No, well, not really. But it's actually the same as and, right? Well, we don't have to or, but this, what we want to say is that or but not and is the same as saying or and not and. Yeah, in English we use the term but in Boolean algebra, in logic, we just say and, right? Or and not and. Yeah, so you can write this as and. That's right, yeah. Or and then not and. So let me just say or is simply, we already have or, yeah? It was just y1 hat, right? Not and is bar of y2, yeah, the complement of y hat 2. Okay? Everyone agree with this? Yeah. This is exactly the Boolean function to express the idea, the definition of exclusive or. Yeah. Okay. So now that means you have to have an m function outside, and then inside you have two perceptrons that we have built before, right? So let's say we have the previous two perceptrons. Do I? No, because I have the same input here now, so I'm going to draw them slightly differently. So let me draw them in this way. So this one, I mean to get y1 hat as output. This perceptron, let me, same size circle. This one, I need to get the y2 hat perceptron. And then let me say I have this H1 here, H2. But H1, H2 also contributes to the first one. We also have to have H0, right? So let's say H0 is something like this. This is H0 equals to 1 always, yeah? Maybe I'll move it down a little bit. I have space. I have infinite amount of space. So just like that. And remember this one was just a bit better. The weight for the OR gate is it's 1.5, yeah? The N one is the -1.5, yeah? So this one is the OR one, right, from before, yeah? No problem, right? Slightly changing how I draw the lines, but they are the same thing. And then for the N one, we also have this, let's say H0 have to go in there as well. Let's say, how do I draw this in the most sensible way? These one come in like that, yeah? The weight here is -1.5 now, yeah? Right? That's for the AND gate. Everyone agree, yeah? So once I draw this, one has this, then the outside output is y2 hat, yeah? So now I have these two, and then I need to build the N 1 as well, right? So the outside n function, that would give me y3 hat, yeah? So y1 comes in, and y2 hat comes in, yeah? Except that the weight here for y2 hat has to be -1, right? And then for the, let's call this y hat 0, yeah, because we always need the augmentation, right? It's always equal to 1. And then what is the weight here? What is the weight for that y hat 0? 1? Are you sure? Yeah? No, this is bias. We have to have the bias. We are building an AND gate, remember, right? This layer here, the last layer here is the AND gate. Minus 1.5, yeah? So minus 1.5 here. Okay. That's it, right? This is the diagram to represent the function above, yeah? The top over there, y3 logical function, okay? And this turns out to be our exclusive OR function, yeah? This is input, the output would be the exclusive OR of H1, H2, okay? Yeah. Almost like what you might have seen in the hardware course, right? When you have to build a exclusive OR gate using your transistors or whatnot, yeah? To get that logic in hardware. But this is all in software, yeah? All in terms of just mathematics, okay? So this is, in fact, our first multi-layer perceptron, right? There we have, at least 2 layers, not a single perceptron anymore. Yeah. In fact, you can view this as a 2-layer neural network if you want. So there we have our first neural network for this course, anyways. Yeah. We call it 2 layers because you have 1 layer of perceptrons here and then another layer of perceptrons there. Okay, 2 layers. Everyone okay so far? Yeah. So one thing to know is that just a note that in the textbook it uses a slightly different formula. Yeah, in the textbook it uses exclusive OR is this y hat 3 equals to OR. And then AND H1, H2. It does not directly use the previous perceptrons. Yeah, it uses this new thing, not H1 and then H2 like that. Okay. Just another way to express the same thing, right? And you can build this as well using a 2-layer perceptron. Yeah, 2-layer, yeah, multi-layer perceptron. But I just find it probably easier just to reuse what we already have. Yes? Yes. Yeah, because in our formula, this one, the Elm function is this one. Right? Yeah. For the Elm gate, for the Elm function, we need to have a bias of minus 1.5 there. Yeah. Now, this has not solved our problem yet. Remember at the beginning, our problem is to say, well, if we have data points, this is X space, right? These are X space data points. That looks like that. Can we separate them using multiple layers of perceptrons, right? So far, we have built logical functions only. We still have to find a way to work with the X space, right? Okay, that means what? We have to have a way to go from the samples to our H functions, H1, H2 functions, okay? And then we do the logical combination of the different regions. Yes?
So is the idea to, whenever you have something, let's say like that,
Mm-hmm.
continuously transform it or get logical functions out of it?
Yeah, for now, we are just trying to show that this way of building multiple perceptrons would be able to separate data points that looks like this, okay? we don't exactly use this N and O in neural networks. Yeah. So therefore, to go to, so that we can create a mapping from X to the labels Y, we need another layer to map from X to H, right? So we need one more layer. Yeah. The functions H1x and H2x. Okay. For example, if we have already two lines defined by the following perceptrons, H2. So this is a example of a mapping, right, from the space to the H values. So what do they represent? H1 would be so X1, X2 here, yeah. And what is H? Would be H1, yeah. This is H1, right? This is yeah. This side would be H1 is +1, right? The other side will be -1, yeah. So the intercept is just 1, right? That's our first line, H1. And then what is H2? It's minus X1 and then plus X2. So it's a diagonal line, right, with intercept of 2. So it looks like this, yeah? And this is -2 and 2, yeah? What are the directions of the +1s? How do I know, say, which one is the +1 direction? Someone tell me? Is it up or down or left or right for this line? Which side is the, someone else? Anyone? You need to know this, okay, because it's important. Which side is the plus, which side is the minus? For this particular perceptron, right? For the H2 perceptron. Yes? No, there's no such convention. Be very careful. That's what the point I want to make, yeah? It's not conventional, up or down, okay? No convention such, yeah? How do we know? You take the gradient, yeah, that's one way to do it, yeah? Basically, when you take a gradient, you just get, -1, for example, yeah? That will work. But you don't have to, you don't even have to be, use such a complicated method, okay? You just like take 1 point for any of the regions. Yeah, you can do that. Yeah, you can say pick 0, 0, yeah? And then you substitute there, 0, 0 give you +2. So you know that this point will be plus. Therefore, this side is plus, yeah? This is one easy way, yeah? Another thing to do is to say, I'm looking at X2, X1, yeah? I move left or right, basically, right? X1, move left or right. If I move to the right, but my X1 is getting bigger and bigger, but then because it's negative X1, right? The value of the function will get more and more negative. When I move this direction, I get more negative. So this side is negative. That side is plus, okay? Yeah? So that's how, there are multiple ways to find out, but they're all simple algebra work, right? Very simple algebra work, but you need to know how to do it. Yeah? So H2 is plus. Yeah? Again, this is not by convention, okay? This is by the way that we write this H2, okay? Notice that I can write the same line if I change this H2 to X1 minus X2 minus 2. Okay, basically I'm multiplying -1 to everything. I have the same line, but then this side will be positive, okay? Be very careful about this point. A very common mistake in previous years, yeah? Yeah. In that case, this one, pretty much, right? Well, in that case, the line was still in this direction if you -1, -1, right? -1, the line would be in this way, yeah. Yeah, and then the plus would be on this direction. Yeah. Okay. So now, if we have these two lines, we can combine them to implement the following rule. Yeah, let's see. Yeah, so now we can implement decision rule as follows. That has both of them. taken into account. So x1, x2, okay? Now this is our space. But let me draw those two lines back. So we have this, like that, yeah? And then the other one is 2, so something like this, yeah? Okay. Suppose, just like our first example at the beginning, right? We have the pluses here, remember? Pluses here, yeah? Right, like that. And then we have minuses, there, right? So how do we find the decision rule for this? We say, well, we know that in this region or that region, right? So what is this region? So our, let's say, y, yeah, equals to plus if what? We know that for our data points, y is equal to plus if, with respect to the h1, h2, yeah? Yeah, h1 has to be negative. With respect to h2 has to be positive. Yeah? So basically it's not h1 and h2, right? So it has to be not h1 and h2. Yeah? That's for the right-hand side region. Yeah? And for the left-hand side region, we have y is plus 1 if what? The right-hand side region? Yeah? You? Yeah, h1 and not h2. Yeah? Everyone okay with this? Okay, so this is h1 and not h2. Okay, those are the two regions where we get pluses. No other, every other region will be negative. Yeah? Okay. That means what? You can combine this to say that this is or, right? Either one of these two regions will be plus, right? Or these two. So the left-hand side is and h1 complement h2. No, not plus. And exactly, very good. Yeah. If you look at this and compare with the textbook's version of the XOR, yeah, same thing. Okay. So this is simply exclusive OR of h1 and h2. Yeah, everyone okay? So it turns out that if we have two lines, that's how we do it. Yeah. Now we can separate two lines, can separate your space into 4 different regions. Okay. And so if that's your data point, then I can represent this training data points very well by combining exclusive OR of h1 and h2. Okay. So, but how do I draw this picture from mapping from x to y? Yeah. We already know how to map from x to h, right? X to h is just those two lines like that. And then from h to y is exclusive OR. Yeah, we also know how to build it. Yeah, we already have it from previously. So I can just copy and paste from before. Very nice. I already have this. Copy this whole thing over. Out of space. Not so fast. Okay. All right. So I'm going to paste it here. These are exclusive OR of the h values, the h. Yeah. And then now I just need to put the perceptron to generate h. Yeah. These two lines. Yeah. Just have to draw these two lines. The perceptron, draw the perceptron for these two. Yeah. So again, they are both x's. So I'm going to erase this a little bit later because, oops. This is still going to be h1. Yeah. This is still going to be h2. Yeah. But now they are the outputs of perceptrons. And the perceptron, the inputs are x's, yeah? So one of them, x1, there's another one, x2. X2 goes there, yeah? And then we also have these, some bias or the always equal to 1, right? Yeah. And this line is, what is that? The weights are 1, 1, minus 1, right? The weights are 1, 1, minus 1. So this is simple minus 1, and then the other lines, I don't have to draw anything. Yeah? That's how we get to H1. Yeah? For H2, it is minus 1, 1, 2. Yeah? Minus 1, 1, 2. Remember? Yeah? Minus 1, 1, 2. So this one will be minus 1, and then 1, and then this one is 2. Yeah? This 2, like that. Okay? Then we're done, right? So basically, this diagram represents the logical function that helps us map x to y exactly for this situation. Yeah? Exactly what we wanted from the beginning of today's class, right? That's what we wanted to map. Find a rule, decision rule to map this training data to the proper labels. And that diagram does exactly that, right? Everyone agrees, yeah? This one does exactly what we wanted at the beginning without any error, right? Okay. And this is our proper neural network then, right? That goes from the input that we want to the label that we want. Okay. So this is there are 3 layers. We have some names for them. This is called input layer, even though we don't count it within the 3 layers. We still call it a layer anyways. This is a hidden layer 1. It's hidden layer in the sense that you don't see them, right? You see the input, you see the output. You don't see whatever that's in the middle. Yeah? Hidden layer number 2. And then we have an output layer. Yeah? Altogether, even though it sounds like there are 4 layers, right? The convention is called this a 3-layer multi-layer perceptron, yeah? A 3-layer MLP. We do not count the input. Yeah, just the same terminology as in neural network. Okay. Yeah. Any questions about this? Yes. Yeah. We just count the neurons, right? The perceptrons. We have 3 layers of perceptrons. So it's a 3-layer multi-layer perceptron. Okay. So again, this would be our kind of a preliminary neural network. Yeah, that's exactly what we want. Of course, the question is how do we know that those lines are the right lines to use? Yeah, here. This is based on those 2 lines, right? I tell you because I'm the one who designed this example. I know those lines will work. Okay, but in reality, when you are only given those data points, how do you know that those are the 2 lines that will work? Okay, and that involves some training, and that requires a learning algorithm. Okay, which we have to talk about that later. Yes.
So for this problem, you can, I guess you can perfectly classify the points within 3 layers.
Mm-hmm.
But suppose, what would happen in this case if you were to use, let's say, 4 layers?
Yeah.
Just keep adding layers.
You could, yeah. That's deep learning.
Would that affect I'm curious if that would affect like sort of the correctness of the classification at the end?
Very good point. So now we're talking about when is it correct? How can I build this in order to maybe fit any function that I want? Yeah, how correct would they be? Turns out that 3 layers is sufficient to approximate any function that we care about in reality. Yeah? Any practical function can be say approximated, or in fact approximated as close as you want by a 3-layer perceptron, if you have enough perceptrons.
So
okay.
Does that mean that just the idea of just adding more layers is just to try to get more?
Yeah, it has some purposes. Yeah, there's some advantage of doing that. We're going to talk about that for the neural network. Yeah, and that will be a topic for discussion next time. Okay, under what conditions this will work, and how can we improve upon this, so that we can train the neural network to recognize data points, so that I don't have to give you those lines to begin with. Okay, so we'll continue tomorrow. Yeah. Yes.
Minus 1.5 weight
Mm-hmm.
for the bias term.
Yeah.
The question that my friend asked. Just wondering, even though it's also an athlete, how do you still
Well, you don't have to use the same way, but all that you need is to build an AND gate, right? For all gates.
Okay.
You can use any number.
Oh,